In this section we're going to be looking at the polar coordinate system. We look at the polar coordinate system because some graphs are easier to describe in a polar plane rather than a Cartesian or rectangular plane. And also in Calc 3, a lot of times you're working with double and triple integration, and you'll be switching between the rectangular coordinate system and the polar coordinate system. So it's a good idea that we have a look at that before you get into those integrations. The polar coordinate system, kind of think about it as similar to an xy plane. This point in the middle is the origin, of course. It's also called the pole, or the middle, or the origin right here. And then what I have from here are concentric circles. So this is out 1 unit, here's 2, 3, 4, etc. So this would be 1, 2, 3, 4. So think about these as radius. Now also part of this would be our angles. So here I'd have pi over 4, 3 pi over 4, 5 pi over 4, and then 7 pi over 4. You'll kind of get the idea here. Here's pi over 6, 7 pi over 6, 5 pi over 6, 11 pi over 6. And then another nice standard angle we always work with is pi over 3, of course. And what I'm doing by looking at the pi over 3, and then I could move up into this quadrant right here and call 2 pi over 3, of course, but I like to pop down into this quadrant. It's kind of the opposite of the pi over 3. So here we are at pi over 3, 2 pi over 3, 3 pi over 3. Here would be 4 pi over 3. And then, of course, if I extend this out, this would be 5 pi over 3. And then I have my quadrantial angles, so I'd have 0, pi over 2, pi, 3 pi over 2, and then 0 back to 0, or we could call this 2 pi as well, of course. So this is my polar coordinate system. Now in the polar coordinate system, again, I have these concentric circles that kind of go out a particular radius from the pole or the origin. Now when I talk about the points of a polar coordinate system, my point is r theta. Okay, so r is a radical coordinate, or sorry, a radial coordinate. Meaning how far out are we moving from the pole, and it's assigned or directed different distance from the pole or the origin. Now when we say signed or directed, it could be positive or it could be negative, and we'll talk about what that means, whether they're positive or negative. Now theta is some sort of an angular coordinate. And we put these two pieces of information together, and this is how we're going to be plotting points. Now it's important to remember that in the polar coordinate system, points have more than one representation. This is because, of course, we can make multiple turns around the Cartesian coordinate system or the polar coordinate system, and we can also move in the positive and the negative direction. In the rectangular plane or the Cartesian plane, those words are used interchangeably. If I talk about the ordered pair 2, 1, that's the only way that I can describe 2, 1 in the Cartesian or the rectangular coordinate system. So in the polar system, I can use more than one way to describe a point. So to kind of show what that is, let's go ahead and look at some points. Now because we're working interchangeably in the Cartesian coordinate system or the rectangular and the polar coordinate system, we always have to make sure about the point that we're talking about, whether it's polar or rectangular. Usually it's pretty obvious, but not always. Let's go ahead and plot some points. So we're going to plot the point A, and it is a polar point, so I'm going to write the word polar here just to give me that reminder. 1 pi over 2. Now this doesn't look like it's easily confused with a rectangular system, because a rectangular I wouldn't see an angle here. So if we look at our coordinate system, it looks like my r is going to be 1 and my theta is pi over 2. So let's go ahead and worry about setting this up. Here's my pole or my origin. I'm going to go out 1 unit. Here's 2 units. So this says in my radius I'm going to be on this first circle. The reason I'm on the first circle is that it is 1 radian, or 1 radius, 1 unit radius out from the pole. So my point is somewhere on this first circle. Now then I go from here and I plot the point pi over 2. So I plot pi over 2 out here on that first circle. Now the interesting thing that we can look at is this is our polar coordinate 1 pi over 2. It's very easy to see rectangular. This is 0, 1. So my rectangular, I can look at this and say, oh, that's the same as the ordered pair 0, 1. And again, this is x, y. We're not talking about our theta here. So again, this is x, y. Now that's not always easy to determine. In this particular case it is. Now let's talk about how we can write these different ways. So we talked about 1 and pi over 2. Let's go ahead and write this point several different ways. I can write it with a positive r. Remember, these are r and theta. Negative r, positive r, negative theta, all these different combinations. So let's look here and let's look at this point. Now I could say that I'm always 1 unit out, so my first value is either going to be 1 or negative 1 all the time. Now the next thing, if I talk about this point, I could have also reached this point not going by pi over 2, but by starting at this point over here and moving 3 pi over 2 in the negative direction. So I could also write this point as 1 and then negative 3 pi over 2. So this would be another way to describe that same point. Now I could also go another direction. Let's worry about making this 1 into a negative 1. Well, what does a negative radius mean? It means to move in the opposite direction. So if I'm moving and I'm plotting this point and I'm thinking about, okay, I want to look at this point. I'm down here at negative 1 and I need to flip back up here. That's the effect of the negative 1. So how do I get down to this point? Well, I could look at this a couple different ways. This could be 3 pi over 2. So starting here, I can move down 3 pi over 2. And then once I get there, I'm at this point right here. And I have to say, well, wait a minute, I don't want to be down here. I want to move across to this point. And so that's what the negative 1 does. It moves it straight across. So I could also look at that same point as negative 1. And then instead of 3 pi over 2, I could call this point negative pi over 2. So if I were to plot negative pi over 2, negative 1, this would be negative pi over 2, positive 1, and then the negative would flip it back into this direction. I could also plot this, I could call this 5 pi over 2, because here's 1 pi over 2, 3 pi over 2, 5 pi over 2. So this could be 1, 5 pi over 2. And I could also do this one down here. I could also call this negative 1. And this could be a negative pi over 2, negative 3 pi over 2, negative 5 pi over 2. Now these are just a few examples. There's an infinite number of examples for these. Now again, for this one, the rectangular was very easy to look at because it was 0, 1. You know, there was no strange angles or anything else that we were working with here. Okay, let's go ahead and look at another point. This point will be point B, and it's a polar point. So I want to make that very clear. And it's the polar point negative 3, 5 pi over 6. So the first thing that we'll do is we'll put up our coordinate system. Now remember, this coordinate system does relate to the xy plane as well. So if you want to put out your x and your y values here, the xy plane, you can, because they do relate, and we'll see how they relate in some examples a little bit further on. So here we are 1 radius out, here's 2 radius out, and here's 3 radius out. Now on a test or a quiz, handwritten homework, you will need to be able to plot these points and be able to work back and forth with these. It'll be really important, but basically it's just some trig. Okay, so 5 pi over 6. So the first thing that we do is we plot the point 5 pi over 6, and we know that we're out on this third ring somewhere because radius is 3. So just as a quick reminder, this is r and this is theta. So I'm out on this third ring, and here is the point 3, 5 pi over 6. And then what I do is I draw my radius straight across here. It turns into a diameter after it hits through the pole, and this would flip over to the actual point of -3 5 pi over 6. Okay, so I usually plot it with the positive r first, and then I worry about running it back through the pole on the diameter to find the -3. So this is a +3 5 pi over 6. This is where it's negative down here in that fourth quadrant. Well, let's go ahead and plot that point several different ways. Let's rewrite it several different ways. So I could have positive r, I could have negative r, I could have positive theta and negative theta. So for instance, let's stick with that -3. What's another way that I could move across this angle? So if I made this a -3, I'd have to flip it from here. If I started here, this would be a -6 pi over 6. This would be a -7 pi over 6, and then the -3 would flip it across. So I could call this -7 pi over 6 would be another way to describe that point. Another way I could make the 3 positive. So if I made the 3 positive, I would just need to work with that angle, which looks like it's a negative pi over 6 then. So 3 negative pi over 6. I could also call it 311 pi over 6 would create that same angle. And you know, there's just so many different ways that we could look at this. I could also make this a -3, and then I could look at, here's 2 pi, which would be 12 pi over 6, 13, 14, 15, 16. This would be 17 pi over 6 would be another way to describe that. And again, there's an infinite number of these, so you know, this ... means there's a lot more of these to choose from. Now here, the rectangular, I'm not so sure about. I don't think this is going to be very easy. It's probably not out exactly 3 units, because 3 units is out here, and not every point on this circle has an x value of 3. So I'm not sure about this. So rectangular, I don't know. We'll have to work on that one. Okay, let's do one more example where we're doing points. This will be the point C. The polar point C would be 2 and 3 pi over 4. Okay, so I need to have a polar system. If I want to put up the x, y, I can. And I need to go out to that second concentric circle. 3 pi over 4 is over here in the second quadrant. So I'm 2 units out. But basically what happens, this is my angle 3 pi over 4. So this is my point 2, 3 pi over 4. And just like we've done before, we want to go ahead and write this several different ways. Now one thing I notice here is the rectangular is difficult as well. I'm not sure what this would look like as a rectangular. Definitely a negative x and a positive y, but beyond that it's not really obvious. Okay, so let's go ahead and write out several values here. So for C, I have the 2 and the 3 pi over 4. And then let's go ahead and write that several different ways. Some with a +2, some with a -2. Okay, and then some with a +3 pi over 4, some negative. And then what ends up happening here is when I look at this angle, this 3 pi over 4, I think, well, I could also look at a negative angle that's running clockwise. So this would be -4 pi over 4. That would be a -5 pi over 4. So that would work. So let's put that one in, -5 pi over 4. Now let's go ahead and jump down here and do that +2 again. I could do something like 2 and 11 pi over 4. Now where did the 11 pi over 4 come in? As I rotate around, I have 1, 2, 3 pi over 4, 4, 5, 6 pi over 4, 7 pi over 4, 8, 9, 10. This would be 11 pi over 4. Okay, so we're just talking about a full spin around the unit circle with an additional 3 pi over 4. Now let's go ahead and talk about these negative radius. Now for the negative radius, I need to plot my point and end up here, and then the -2 pops it back into the second quadrant. So this angle would be a negative pi over 4. That would be one problem that we could look at. And then I could also look at this as 4 pi over 4, 5, 6, 7 pi over 4 as well. So these are all different ways to name the same point in the rectangular coordinate system. And again, for the B and C that we did, it's not real clear to me what the rectangular XY value would be. So let's go ahead and look at how we would convert between the rectangular and the polar to rectangular. So what we'll need to know are a couple of interesting trig facts. I love these sections because it's just a nice look at trig. We're really not doing a lot of calculus right now. So we're going to convert between the Cartesian. In our textbook, in the problems that you'll see the Cartesian, but you'll also see in a lot of other books rectangular coordinate systems. So I want you to be familiar with both of those. So converting from Cartesian / rectangular to the polar system, and vice versa. Okay, so to convert, let's think about a point that we'd end up with. So let's say we have this point right here. And in our polar system, this is r units out, so there could be several concentric circles here. And then I'd have this value of theta. So if you think about this, x would be my distance along the horizontal, y would be my distance around the vertical, and this would be a right angle. So this is a right triangle. So if you want to think about SOHCAHTOA, you could do that. Side opposite over hypotenuse, or sine opposite over hypotenuse, cosine adjacent over hypotenuse, tangent opposite over adjacent. You could do all those. And if you're used to unit circle trig, you could think about the cosine of theta then would be x over r. And if you want to think adjacent over hypotenuse, you can, or just remember that ratio. Well, if we solve for x, we get x is equal to r cosine of theta. And again, this is straight from unit circle trig. Now the sine of theta would be opposite over hypotenuse, y over r. So solving for y, this would r sine theta. Now this is how we convert back and forth these two formulas, x equal r cosine theta and y equal r sine theta. Now this would be if we were given a polar, an r and a theta, and we had to convert back to rectangular so we could find x and y. Now how do we move from rectangular back to polar? Well, to move in that direction, what we would use is the Pythagorean theorem, x squared plus y squared equals r squared in this case, based on my triangle here. And then we'd use a trig ratio. Tangent theta is equal to opposite over adjacent. So y over x. Now we could use sine or cosine here as well, but sine or cosine would be dependent on me finding r first, and if I found r incorrectly, then that would throw off those other trig ratios. So a lot of times we just like to go ahead and stick with tangent, but you could use sine or cosine here as well. So these are the formulas I'd use for rectangular or polar, and I should write up here then that this is what I would use for polar to rectangular. So I'm going to scoot these down a bit so I have enough room to put in that heading. So this is what I would use for polar to rectangular. So let's go ahead and look at the problems that we just had and that we just graphed, and let's go ahead and convert them. So remember, we had the point A that was in polar form, and the point in polar form was 1 pi over 2. And so what we want to do here is convert to rectangular. So recall, this is r and theta. So the formula that we have for x is equal to r cosine of theta. So to find my x coordinate, r would be 1, theta would be pi over 2. Well, the cosine of pi over 2 is 0, so 1 times 0, my x coordinate would be 0. Now my y is equal to r sine theta. R is 1, theta is pi over 2. And of course, sine of pi over 2 is 1. 1 times 1 is 1. So this is my ordered pair 0, 1. So if I were to plot this, it would be right here at 0, 1. Now if you recall, this was my polar coordinate 0, 1. So that totally makes sense with this particular problem. Now let's go ahead and do the same thing for the second point B. And I always like to plot them when I'm done, just so I can see if they're kind of ending up in the correct quadrant and seem reasonable. So the polar point I have here was -3, 5 pi over 6. And I want to convert to rectangular. So the way I start converting to rectangular, I use x is equal to r cosine of theta. R is -3. Theta is 5 pi over 6. Now the cosine of 5 pi over 6, if we know our unit circle, this value is pretty easy to come up with. 5 pi over 6 is in the second quadrant, so the cosine is negative. So this would be a negative square root of 3 over 2. So my x value here, negative times a negative is a positive. It's 3 root 3 over 2. I don't need a decimal approximation. I'll just leave it as x is 3 root 3 over 2. Now just like we did up here, we now do y equal r sine theta. Plugging in my values, r is -3, theta is 5 pi over 6. 5 pi over 6 is in the second quadrant where sine is positive, so the sine of pi over 6 is positive 1/2. So my y value then is -3/2. So just like we did up here, let's go ahead and plot this. So my ordered pair is 3 root 3 over 2, -3/2. Now I'm not exactly sure exactly where this is, other than it's somewhere in the fourth quadrant. So I'd be somewhere over here in my positive x and then negative y. Now if we look up at our point that we graphed before, we'll see that it was also somewhere over here in that fourth quadrant. So that's a ballpark idea that, yeah, these numbers seem to be turning out okay. Let's go ahead and look at that third one that we had, point C. Point C was a polar coordinate, 2 and 3 pi over 4. And let's go ahead and convert to rectangular. So we do the same, x is equal to r cosine of theta. R is 2, theta is 3 pi over 4. That's in the second quadrant, so cosine is negative. So this is negative square root of 2 over 2. The 2's cancel and I'm left with negative root 2 for my x value. Now let's go ahead and do y equal r sine of theta. R is 2, sine of 3 pi over 4. 3 pi over 4 is in the second quadrant. So sine is positive in the second quadrant, so this is square root of 2 over 2. The 2's cancel and I'm left with y equal root 2. So my point here would be negative root 2, positive root 2. So if I were to just give this a quick sketch, this would be negative x and then positive y. So it would be somewhere over in the second quadrant. So let's go ahead and have a look. Yep, somewhere over here in the second quadrant. That works perfect. So that's an example of converting all of our polar points to rectangular. Now the reason I always write what the point is, polar or rectangular, let's go ahead and look at a point D. What if I had the polar point, or what if I had the point, let's do something like -2, 4. This looks rectangular, but this could be 4 radians, I don't know. This could be a radius of -2, I don't know. So you don't always have a multiple of pi here, so you have to kind of be careful about that. So I could have -2, 0, and this definitely looks like it's rectangular, but it's a polar point just because I say it's polar. So this is an r and a theta. So you have to be very, very careful to identify which is polar and which is rectangular or Cartesian points. So let's go ahead and take this polar, and converting this is really easy because I have a 0 here. So if I plot this first, this would be -2, 0. On the Cartesian coordinate system or the rectangular system, if we convert to rectangular, I'd still have the same point, -2, 0. So sometimes it turns out like that, but it's always important to state that it's polar. And the reason we want to state that it's polar is so we don't get confused with rectangular, because it looks like it could be a rectangular point as well. Okay, let's go ahead and look at a point E. This is a rectangular point, and this is a rectangular point 1, negative 1. So again, I always like to plot these first just to kind of get an idea where I'm at. We haven't plotted these yet. So this is 1, negative 1. So it should be somewhere down here in the fourth quadrant. So what I'm going to start with is I need to find this radius. So I'll start with x squared plus y squared equals r squared. So I'll have 1 squared plus negative 1, make sure it's in parentheses, quantity squared equals r squared. 1 plus 1 is r squared is 2. R could either be a positive or negative root 2. In fact, it's probably going to be both if I want to write this point in multiple ways like I know I can for the polar system. So again, I should put my directions here, convert to polar. Okay, so next thing I will do, I'm going to look at the tangent of theta is equal to y over x. So tangent of theta. Okay, now y in this case is a negative 1, x is 1, so I get tangent of theta is negative 1. So I'm going to go ahead and take the inverse tangent of both sides. Or arctan, if you want to think about it like that. And this means what angle in the interval negative to positive pi over 2, points not inclusive, has a tangent of negative 1? And the answer is negative pi over 4. Now this is my reference angle. I kind of build everything off of this. So I have the two pieces of information I need here. Now I kind of have to put them together. So let's say I want to do this and I want to have an r and a theta that are both positive. Okay, so if I want to have a positive r, this would be a positive root 2. And then my theta, I'd have to start here and move clear around to 7 pi over 4. So that could be one solution. Another solution could be root 2 negative pi over 4. That would work just as well. But what about a negative root 2? So that would be this point from up here, and it would reflect straight down here. So that would be, let's say, 3 pi over 4. Negative root 2, 3 pi over 4. Let's do another one. Negative root 2, negative 5 pi over 4. So there's a lot of different ways to write these. It's kind of fun to see, to make sure you can get a few combinations of a couple positive r, a couple negative r. Make sure you have some where they're both positive or both negative as well. Okay, let's go ahead and look at some basic curves in the polar coordinate system. Now the reason that we look at some of these curves is it's a lot easier to use the polar coordinate system to describe some of these. But we also have to be able to work back and forth while we're looking at these. So a couple of basic polar equations. So I'm going to look at the polar equation let's do r equal 3. So that means the radius is always 3. Okay, and theta is arbitrary, meaning it doesn't matter what theta is. So theta could be anything here. So I'm looking for a graph where the radius is always 3. Well, if we think about that, the radius could always be 3. That's a circle. And this particular circle is centered at the origin or at the pole, if you want to look at it like that. And of course the radius is 3. So this is a nice circle with a radius of 3. Now notice I could look at this as r equal negative 3 as well. Depending on where I am down here, I could flip across. So I'm really just looking at the absolute value then of 3, or the absolute value of negative 3 to just get r equal 3. So if I have a negative value for r, I can still work with that. Let's go ahead and look at another polar equation that you might come across. So over here, r was 3, that was a whole equation, and theta was arbitrary. Now this one, I have theta is pi over 3, let's say. And in this particular case then, r is arbitrary. That means r could be any value. So as I'm graphing this, I have to think, okay, where is pi over 3? Well, here's pi over 3. Well, that could extend in either direction, because I could have r could be positive, so I'd be up in this region. R could be negative, so I could be down in this region. What's important is I have this angle. And so this is my graph of theta equal pi over 3. Now again, up here would be my positive r, down here would be my negative r. So those are a couple. My favorite, well, not my favorite, I love these polar equations, they're really fun to work with. But one of my favorite polar equation would be when r and theta are equal. So what this means, they're kind of both arbitrary. You know, as one changes, the other one changes as well. So what's happening here, as r gets larger, as r increases, theta increases. And this creates a spiral. Now you could plot some points to figure some of these out, but a lot of these aren't very intuitive. So what the spiral starts to look like, let's look at 0. So 0 radius, 0 degrees, or 0 radians would put us at right at this point. And I could look at 1. So I could look at the radius of 1, and then look at the theta is equal to 1 radian. And what ends up happening is this starts to spiral out. Okay, and so this is what r equal theta looks like. Now, if you change this to r equal 2 theta or 2r equal theta, you're going to have some changes on that, but these are kind of our basic parent graphs that we go off of. So let's go ahead and think about, you know, these are not intuitive graphs for us. Let's think about like taking this graph and converting it to the Cartesian coordinate system. Let's look at this graph and convert. Let's think about this graph and see if we can convert. So how do we convert those graphs? So we're going to be doing converting equations. And each one of these has a bit of a trick to it, so you kind of have to look at it to determine, you know, what could I do with this one? There's not a hard and fast rule that will work for every single one. So to get started here, let's go ahead and look at the polar equation. And let's do r equal 5 sine theta. Okay, well we're trying to get this back in terms of x and y. So if you recall, y is equal to r sine theta. So if I could just get an r in here, I could do some converting. So I'm going to multiply both sides by r. So I have r times r on the left, and here I have 5r sine theta. So if you notice, we have r squared equals 5, and then r sine theta is equal to y. But we also know from previous work that r squared is equal to x squared plus y squared. So I have x squared plus y squared equals 5y. And I'll go ahead and subtract that 5y across, and I get x squared plus y squared minus 5y equals 0. Well, this doesn't look like a circle, but it is, and the way we find it and put it into standard form is by completing the square. So let's go ahead and look at this and complete the square. So x squared is good. We don't need to do anything with that. Now over here, this would be y minus 5 halves quantity squared. And I would have had to add 25/4 on both sides. So this would look like x squared plus y minus 5 halves quantity squared equals 5 halves quantity squared. So this is a circle. Center at 0, positive 5 halves, because you always do opposite here, with a radius of 5 halves. Okay, so that works pretty slick. This one was nice and easy to do, but basically that's what you're going to be doing, is trying to look at that and see if you can convert it back using some of these tricks. Now polar equations can describe curves that are different to represent, or difficult to represent in the Cartesian or rectangular coordinate system. So to me, it's easier for me to look at this equation and say, oh, that's a circle, than it is for me to look at this equation, because we just haven't had as much experience with that. Now let's go ahead and look at how we would graph some of these. So let's go ahead and look at how we graph. Basically, we plot points, but the problem with plotting points is if you skip any, you might lose some very important features of a graph. So let's go ahead and look at r equal 2, let's make this easy. Well, yeah, we'll do 2. 2 plus sine theta. Now if we want to think about this using functional notation, this would be the same as r equals f of theta, just like we would use f of x, 2 plus sine theta. So we'll plot points. Now remember, when we graph points, we like to have r first and then theta. So this is going to look a little bit backward. I'm going to have my different values of theta over here, and then r is 2 plus sine theta. Okay, so theta, I'm just going to choose some nice angles. I'm taking the sine of all of these angles, and if I take the sine of a multiple of pi over 4, I get square root of 2 over 2, and that's not an easy thing to graph. If I use sine of pi over 3 or a multiple, that's not easy to graph either, because the sine would be square root of 3 over 2. So I'm going to stick with multiples of pi over 2 and pi over 6's. So then I'd be at pi, 7 pi over 6, 3 pi over 2, pi over 6, and then I'm back to 2 pi. Okay, so again, I just chose these values because they're easy values for me to evaluate and graph, because it's hard to graph square root of 2 over 2 or something like that. Okay, so let's choose 0. So the sine of 0 is 0. 0 plus 2 is 2. So this is the ordered pair, or sorry, this is the polar pair to 0. Now pi over 6. The sine of pi over 6 is a half. 2 plus a half is 2 and a half. Okay, pi over 2. Sine of pi over 2 is 1. 2 plus 1 is 3. And so we're going to go through and run through all of these, and then we'll plot these points. Pi, sine of pi is 0. 0 plus 2 is 2. 7 pi over 6, that is in the third quadrant. The sine of 7 pi over 6 is a negative 1/2. 2 minus a 1/2 is 1.5. And then again, continuing on, 3 pi over 2 will give us a 1. 11 pi over 6 would be another 1.5. And then I'm back to 2 pi, and sine of 2 pi is 0. 0 plus 2 is 2. So it kind of starts all over again. Now we have to plot these points. It's always hard to get a nice polar graph out here, because those concentric circles, it's easy not to draw a perfect circle, of course. It looks like the largest value of r will be 3, and the smallest value of r will be 1. So I just need to have 3 circles here. So there's 1, 2, 3. And again, I can think of this as my x and my y plane as well. So this is the point r theta. So this is, again, r theta. So this would be the point 2, 0. Now this is not on the rectangular, this is on the polar system. It happens to plot as the same point though. So 2 units out, theta is 0. Okay, then I go 2.5 units out, so they'd kind of be on this circle in between, pi over 6. So here's pi over 6. And again, I'm at 5 pi over 6 as well. I'll just plot all these in right now. Here's 7 pi over 6. And here's 11 pi over 6. And I'll put in my standard angles. This is 0 or 2 pi. Okay, so next point would be 2.5. So that would be 1, 2.5 pi over 6. And so it's kind of curving out, it looks like. Maybe it's a circle, I don't know. And then I'm at pi over 2, 3. So that definitely doesn't look like a circle. It looks like it's coming out and then coming back in. And then here I am at 5 pi over 6, 2.5. And then 2 pi. So I'm 2 units out at pi. It's very symmetric though. And then at 7 pi over 6, I'm at 1.5. And at 3 pi over 2, I'm at 1. 11 pi over 6, I'm at 1.5. And then I'm back to where I started here. So this is kind of a strange shape, and this is called a cardioid. And there's all these cool shapes. There's roses and all sorts of other things as well. But this is a cardioid. Now it doesn't, you don't see this really clearly, but it kind of loops up and then back out. So I'm going to start here and kind of sketch this in. And then it comes in, and then once it comes in, it kind of heads back out in the other direction. And it's kind of hard to show because this is not a real perfect scale. But what happens, it kind of almost has this little indentation and then it comes back out. So it's not a circle. It kind of comes up and then back out again. Well, I want to graph this using some sort of graphing utility. If you have a graphing utility that you use, you can use that. I'm going to go ahead and use Desmos, just because I know it's accessible. So we're going to graph r equal 2 plus sine theta. Well, right now in Desmos we're in the Cartesian or the rectangular coordinate system, so I'll come up here. I'm going to change my grid to the polar coordinate system. Okay, and so now when I graph, I need to not graph in terms of x and y, but in terms of r and theta. So I have r equal, and this was 2 plus sine theta. 2 plus sine, and then theta. I have to put that in parentheses, and I actually spell out the word theta. Okay, so this is the graph of 2 plus sine theta. It looks pretty similar to what we have as well, but you can see how it kind of flattens out right here. And it's kind of hard to tell, but it does smooth up and then go back out. Just trying to see if we could get that to be a little bit more pronounced by changing our scale, but it really doesn't change too much. So you could be given a graph like this, and then based on the graph you could find some information, but I wouldn't expect that you would necessarily be able to graph one of these right off the bat. That was very difficult. A real basic one like a cardioid seems reasonable, but there's some crazy graphs out there. And so while you're working through your homework and your handwritten homework, I really recommend that you graph these just to get an idea, to kind of start getting an idea of what some of them look like. Okay, so that was an example of a cardioid. Now this particular graph is symmetric about the y-axis, and so that's kind of an interesting piece of information. And there's some rules that we can go through and of course memorize if we wanted to. And we could say things like, well, a polar graph would be symmetric about the y-axis if the point r theta is on the graph whenever you have another point like pi minus theta and a negative theta as well. But I just like plotting it and looking at it and determining whether it's symmetric or not. Now we have other shapes as well. We have roses. Kind of look like a four-leaf rose, and so a four-leaf rose, and I'm just going to give you some examples of these because we don't have enough time to plot every single one of them. And it's very tedious to plot a polar graph sometimes. And if you notice, if I had skipped a few of these points, I might not have gotten this flat spot that kind of peeks up here underneath. So you have to plot a lot of points, and if you skip any, you might have kind of a bad curve sketch. So you have to be careful that you plot lots of points. Okay, now from here, like I said, we have a rose. So a rose type of graph would be something like r equal 3 sine 2 theta. And there's nice little patterns you can follow. So r equal, I think I said 3 sine 2 theta. Okay, and so you can see it kind of has this kind of flower pattern. That's why they call it a rose. Now, if you look at this, you can see here's a radius of 4, here's a radius of 3, so that's probably where the 3 comes into play. Let's change that to a 4 and let's see how this changes it. And you can see then it goes out to 4 units. And what if this was a negative 4? I wonder if that would matter. And you can see the negative doesn't matter because each of these points would reflect across. So let's go ahead and leave that as a positive 3 because that's what we started with. So it's kind of neat to change some of these values. Now 2 theta, what if we made that 4 theta? So it looks like when I had 2 theta, I had 4 petals. And now when I made that 4 theta, I have 2, 4, 6, 8 petals. So I wonder if I change this to a 6 if I'd have 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yep. Now our original graph was 2 theta. And again, it's kind of fun to look at these and change some of those values. And when you change those values, you start to see the influence on the number of petals and some things like that. But again, you get these just by plotting points and being familiar with working with some of these. So again, as you're working through your homework, I encourage you to graph these to kind of get a feel for what these types of different graphs looks like. Let's look at another type. This one is kind of an interesting one. It has a particular name. It's called a lemniscate. So for example, we could have something like r squared equals 9 cosine theta. And this is an interesting graph, and it has some interesting characteristics. Up here, I guess we didn't talk about, it's symmetric across the x, across the y, and because it's x and y, it's also the origin. So this has lots of symmetry. Let's look at r squared equals 9 cosine theta. So r squared equals 9 cosine theta. And I don't know, maybe this won't graph it. Maybe it doesn't have the ability to graph something this complicated. So yeah, it doesn't. See my exclamation point here. So it only can be in terms of r. They don't do r squared. So I'll show you a quick sketch. This graph kind of has that flat that the other one did. So this one, what ends up happening with something like this, the square root of 9 is 3. So that kind of makes sense if you think about taking the square root of both sides. So the square root of 9 would be 3. So the furthest this graph goes out is 3, and then it kind of has this circular shape, but it's not really a perfect circle, and it kind of flattens out. Now what ends up happening, of course, this is symmetric across the x-axis. It's also symmetric across the y, and so it also has origin symmetry as well. So again, the best thing to do is to graph as many of these as you can. We already found out that Desmos doesn't graph everything. Some of the polar graphs are a little bit harder to do, but graph the ones that you can because they are very interesting to look at. And again, a graph like this would be really hard to describe in a rectangular system because of this flat piece right here. These are not two perfect circles. So again, please graph a lot of these as you're working through. These are fun little problems, and what ends up happening, we don't have any calculus right now with these. We're just looking at learning about the polar coordinate system, and then we'll get into the calculus a little bit later on. Good luck, and please let me know if you have questions.